Welcome to Texas State University's Chemistry 2330 Introduction to Organic Chemistry. I am your guide, Dr. David Irvin. We will continue on with Chapter 1, Part 6. Okay, so will sum up the rest of the chapter in telling us about covalent bonding and the shape of our molecules. But the thing we're going to talk about now is resonance. Okay, now, when we looked at drawing Lewis dot structures, most of the time we had a single bond and no charge associated with it. But there are times and places where we will see that no one drawing of our Lewis dot structure tells the whole story accurately, meaning that, well, for example, in this case that we see here, why is this charge here and here, but not here, okay? They seem to be equivalent. We don't know that there's any difference there. So this one representation of a Lewis dot structure does not tell the whole story, okay? So we have to have a thing what we call resonance, and resonance are multiple, two or more Lewis dot structures that give an accurate representation of where the electrons are. So in this case here, we can actually take these electrons and instead of having this lone pair here, turn this into a double bond and turn this into the charge, which gives us this structure here. And we can do the same thing and move the two charges to these other two atoms. All three of these are accurate representations of an individual state. However, resonance is saying all three of these contribute equally to the actual molecule, okay? So this happens most of the times when we have ions, but what we'll see is that they can have two or more contributing Lewis structures that will tell us where the charge might be, okay? So when we look at these, we want to use a double-headed arrow to show that two electrons are moving from one atom to form a new bond, and then the one bond is being moved to form another lone pair, okay? So the molecule or ion described by one or two or more of these structures is what we call our hybrid Lewis dot structure, which is all of our contributing structures to the system. Okay, so how do we draw this and how do we kind of get in our heads that these are equivalent structures, okay? So what we want to do is if we take a structure we drew as a Lewis dot structure and we move only electrons, okay? Do not move any atoms, do not break in any bonds between atoms. All we're going to do is move electrons around. And if we can move electrons around to give us equivalent structures, then we have the possibility of resonance, okay? So we're going to just move electrons to show the three different structures that would contribute to this carbonate ion, okay? So in this case here, we are taking electrons from this charged species here, moving them into the to form a bond between the carbon and the oxygen. Notice we haven't broken apart the atoms. We still have the same connectivity between atoms, okay? Now, because we can't have 5 bonds to carbon here, we have to take the electrons from this and move them back up onto the next atom here. So all we've done is move these electrons in between this carbon and this oxygen, and the electrons that were this double bond are now forming the charge on that atom, okay? If we do that same thing again, where we move these electrons in here, we can't keep this bond because it would have 5 bonds to carbon. So we're going to move those electrons out to form our charge on our oxygen species here. Okay, so, and there's nothing that says we can't go in back and forth, back and forth, back and forth between all of these. In fact, somewhere in between is what it really does exist in time and space. Okay, so when we do resonance structures, we always show a curved arrow, a double-pronged curved arrow, showing 2 electrons have moved from where they are, and it's showing 2 electrons moving to where they're going. okay? So you can only do it moving from an atom to an adjacent bond and from a bond to an adjacent atom. You cannot jump across systems. The electrons have to stay attached to whatever atom they were on, and they just move in between other atoms when they move, okay? If you're taking electrons from one side to the other, there has to be a resonance structure somewhere in between. Okay, so when we draw resonance structures, all acceptable contributing structures must have the exact same number of electrons, okay? It must obey all of the covalent bonding rules. There can be no more than 2 electrons in the valence shell of hydrogen, no more than 8 electrons in carbon, nitrogen, oxygen, fluorine. And in the third periods, you can actually have higher numbers, for example, 12 electrons. This comes into play when we use sulfur and phosphorus with our compounds. We'll see that again later. We can have those higher number of electrons in those bigger shells, okay? Notice we haven't changed number of electrons or changed number of bonds. All we've done is show where the electrons have moved from one side of the molecule to the other, okay? We have to have the same number of paired and unpaired electrons, okay? So sometimes we can have an unpaired electron in the system and it will also give us a resonance structure. Okay, so let's do a couple of examples here. There are 3 examples written on the bottom here. And what I'm gonna do is I'm gonna do one of them and I want you to go ahead and do the other one. We did carbonate ion in the beginning here. So what I'm gonna do is I'm gonna do this acetate ion here. Now, acetate ion is we take acetic acid, which is an organic compound, and we remove one of the hydrogens from that and we can get to multiple resonance structures. So let's draw the compound right here. So if we had acetic acid, that would be C, H, H, and H here. And we have to put our lone pairs here. So this carbon here is sp2 hybridized, it's trigonal planar. This oxygen here, when it was acetic acid, we had the 2 electrons that were bonded to this hydrogen here. But what we're going to do is we're going to remove this hydrogen and these electrons become a lone pair residing on the oxygen. And because we have one more electron there, we now have a negative charge here, okay? So this negative charge is on this oxygen because it has a total of 3 lone pairs and 1 bond to carbon, okay? So now that this hydrogen has gone away and left its electrons, we're going to remove it. Now let's draw the resonance structure for it right here. So we are going to do a double-headed arrow saying it can move back and forth between those 2 structures here. And using our rules here, we're going to take this pair of electrons and move it into here. So they're still attached to the same atom, but we're creating a bond here. Now, if we did that, that would have 5 bonds around this carbon. We can't have that. So we can either move these electrons here, but hey, wait, no, that's going to break our carbon-carbon bond. So we can't move these electrons. So we have to move the electrons that are here because the carbon and oxygen bonds still exist and we've only moved the electrons up to there. So that means our resonance structure, and I'm going to draw the mirror image of it so that you can take a look at that. Carbon and O, lone pair, lone pair, lone pair, and a new lone pair. That means the negative charge is now up here. C, H, H, H. Okay. So this would be the equivalent resonance structure for having the electrons move from here to here. So now we've just moved the charge from one oxygen to the next. Okay. Which of these is absolutely right? Neither one. The blending of the 2 together is the actual structure, meaning we have a partial negative charge on this side and a partial negative charge on this side, and somewhere in between is the true structure we actually can see and use in our chemistry, okay? So I want you to go ahead and do that with acetone and the carbonate ion and look for ways you can build these structures without breaking any of the resonance structure rules. Okay, so The last thing I want to talk about here is what we call functional groups. Okay, so we know we can make these sigma bonds with hybridized orbitals, and we know we can make pi bonds with other orbitals, and we know that some atoms will have lone pairs on them and some atoms bond 2 times, 3 times, 4 times, or just once. Okay, now by hooking them up in different configurations, we end up with different reactivities. We have different compounds, they have different properties. And since we can hook them up differently, we have to start naming them different things. So when they're hooked up for a different way, we call them different compounds. And those different types of compounds have what we call functional groups. Okay, so the first functional group I want to talk about is the alcohol. Okay, so the alcohol is whenever we have an oxygen bonded to a carbon, and then that oxygen also bonded to a hydrogen. Okay, so electronically, that oxygen is in that tetrahedral shape, and that hydrogen we can use to do chemistry on there. So an alcohol is an organic compound that has a carbon, oxygen, hydrogen bond. That's the alcohol. Okay. The next functional group we want to talk about are called amines. Okay, amines are when you have a carbon hydrogen, a carbon nitrogen bond. Okay, so nitrogen can bond up to 3 times. So you can have 3 hydrogens on that nitrogen, and we call that ammonia. It's technically not an organic compound because there's no carbon bond in it. We can bond 1 carbon to it, 2 carbons to it, or 3 carbons to it. And we'll see this in chapter 10 when we talk about all the different types of amines, but we have different types of amines that we can use with them. Okay, the next functional group I want to talk to you about is the carbonyl group. Okay, we have several things that involve the carbonyl group. The simplest one is where we have the carbonyl bonded to a carbon and bonded to a hydrogen at the same time. Okay, so we have a carbonyl, which is the C double bond O. It's nice trigonal planar structure. And if it's bonded to a carbon and a hydrogen, we call that an aldehyde. Okay, these are used a lot in biological systems, and sometimes they have cool smells. And so aldehyde is one. Very closely related is to take off that hydrogen and bond it to another carbon. So if you have a carbonyl bonded to 2 different carbons, we call that a ketone. And again, these have nice smells and are used a lot in biological systems. Okay, so the identifier for the aldehyde is carbon and hydrogen, and the identifier for the ketone is 2 carbons here. Okay, is there another way to use a carbonyl group and still have it bonded to other things? Yes, there is. And the first one we're going to look at there is the carboxyl group, or what we're going to do is we're going to take the carbonyl group and put an OH group on it and turn it into what we call a carboxylic acid or a carboxylic acid derivative. So the carboxylic acids are identified by having your carbonyl, your C double bond O right here, bonded to an oxygen and bonded to another carbon here. So the carbon bonded, let's do that right there. So we have a carbonyl oxygen is a carboxylic acid. Carbon, carbonyl carbon is a ketone. Carbon, carbonyl hydrogen is an aldehyde. They're all related to that same group. Okay. So we're going to go into detail about each and every one of these, but I wanted to show you with our Lewis dot structures that by doing the different additions and configurations, we get to different functional groups, and different functional groups gives us different names, properties, and chemistry. Thank you, and that completes our chapter 1 videos.